Everyone, so new plan since I'm pulling this just after the announcement that remote learning goes on for another week has come out. So what we're going to be doing is this lesson, which is going to basically finish off our light as a wave topic, and then rather than just trying to do the stack remotely, we're going to go on and start on our next area of study. So we'll get 2 lessons of that. That'll carry us through to next Tuesday. On Wednesday, when hopefully we'll be back, we'll be doing revision. We'll be doing some of the stuff that we aren't quite able to do remotely, and then the stack will hopefully be on Thursday. So that's the plan. We'll see how that goes, but it just means that we're going to have 2 lessons, one after this and the one after that, where we're starting on the next area of study, which is a short one, but it just means for now things will be a bit muddled. When we're back, we can help straighten them out. Anyway, this lesson is on Young's double slit experiment. There's going to be some stuff in here that I can't really go into just as a PowerPoint. There are some links here. If you use those links, you can do it yourself, but I'll also be going through that when we have our revision lesson once we get back. So it says last lesson was the one before that. In that lesson, light was passed through one slit and we got what was called a diffraction pattern. This is called the double slit experiment. So it's about this lesson, light passes through 2 slits, and there's going to be some physics involved there that's a bit more in depth than what we saw when we only had 1 slit. So if light were to behave as a particle, like we can see in that left picture, you've got the light with 2 slits. Then when it passes through the 2 slits, there should be only 2 areas behind the slits where the light can be seen, where it has passed through the slits. So you should only see its 2 bands on the screen if light has to go through 2 slits, if light is a particle. What you actually see in the double slit experiment is there are actually multiple bands seen behind the slits. This suggests that the light is diffracting, which is a wave-like behavior. So A is the theory, B is what you would actually see if you had the setup right. You'd see multiple bands appearing on the screen, not just the 2 that you'd expect behind the slits. So we're going to look at this in terms of waves. In that picture, you've got the waves coming in from the left. There are the 2 slits there. Some of the wave passes through the top slit, some through the bottom slit, and each wave coming through those 2 slits diffracts around the outside of, and you get those circular waves around the outside of that slit. And what happens is that those 2 waves from the top slit and the bottom slit are going to interfere with each other. So we've got interference going on. In some areas, those 2 waves are going to interfere constructively. They're going to be in phase. They're going to add together, and they're going to produce what we call bright areas or antinodes. In other areas, they're going to interfere destructively, where a peak and a trough happen to overlap, and they produce dark areas, which we call nodes. So we're using the same notation, antinodes and nodes, that we were using back when we looked at standing waves. It's just this terminology is similar. Nodes basically means cancelling out and nothing's there. Antinodes means they add together and you get something bigger. That's what we were looking at when we did standing waves, so the terms do kind of mean the same thing, even if the context is a bit different. So you see those bright and dark bands on the screen. You can see that we kind of designate them by a number n. So we've got n equals 0 for that middle band, and then if we move either 1 up or 1 down, those would both be the n equals 1 bands, another one n equals 2, another one equals 3. There are no negative ones, so it's always going to be n equals 1 regardless of whether you're going to the left or to the right of the central band. So just try and keep this image in your mind, because you'll be seeing it a bit when this pops up, that if you've got, or if you look at those blue lines, for example, you can see that along those blue lines, the 2 waves are going to be corresponding. You've got their peaks matching up with their peaks, their troughs matching up with their troughs. That's where the 2 are crossing each other and their peaks are overlapping. So that's giving you an idea of what these bands actually represent, that at those locations the waves are in phase and they add together. We get constructive interference, we get those bright antinodes occurring. Now I've got a little link here. I'm going to skip this because I'll show you this when we get back. So when we look at the double slit experiment, we use a concept called path difference to explain the formation of antinodes and nodes. So you can hopefully by now understand a bit about why we get those antinodes and those nodes. We're going to use path difference to help explain where we get those bright and dark bands. Now, we've got an equation for path difference. We write path difference as PD because it's shorter than writing path difference. It's equal to the magnitude of S1P take away S2P P is some point on the screen. So it could be M, or it could be N, or it could be R from any of those from the picture down the bottom. And S1P is the distance from slit 1 to point P. S2P is the distance from slit 2 to point P. So we've got some point P. It's on the screen downwind from the slits. We're going to look at the distance from one slit to the point and the distance from the other slit to the point, and we're going to find the difference between those two distances. That's what the next example would be. Yeah, I'll just launch into that. So example's still a ways away. So if the light emerging from one slit travels the same distance as the light from the other slit to get to that point, or travels one wavelength more or two wavelengths more, the waves arrive at point P in phase, peaks match up with peaks, and you get constructive interference, which results in a bright antinode. So in that picture there, you can see that there are two waves heading towards the same point on the screen, and if you look at this, you can see that the top one is going to travel one wavelength less to get there than the bottom one. The bottom one's going one wavelength more in order to get to the same point. So there's a wavelength difference in terms of how far the two waves are traveling. The bottom one travels one wavelength more than the top one travels. So what happens is that we've got a path difference which is equal to one wavelength, and that tells us that we're going to get constructive interference at that point on the screen. We've got this equation which basically tells us that if the path difference is equal to some whole number times the wavelength, then we get an antinode, a bright spot forming. So if it travels the exact same distance to the middle of the screen, which would be like along that middle horizontal dotted line, then we get a path difference of 0. Two waves travel the same distance. They have a path difference of 0, and so you get a bright antinode forming. If one travels one wavelength more than the other, you get a path difference of one wavelength. You get a bright spot occurring there. If it's two wavelengths, then you get a bright spot. If it's three wavelengths difference, then you get a bright spot. This is going to be how we see where the antinodes form. We've got the opposite deal here. So it says if the light emerging from one slit travels half a wavelength further than the light from the other to arrive at point P, or travels 1.5 more, or 2.5 more, something and a half more, the waves arrive at point P out of phase. Peaks from one match up with troughs from the other, and we get destructive interference occurring, resulting in a dark node. So that's what's going on in that picture there. You can see that one wave, the bottom one, is going to travel half a wavelength more than the top one, and as a result, when they get there, they are one's at the screen, one's up and the other's down. They cancel out. That's destructive interference, so we get nothing there. We get a dark spot where there's no light because the two bits of light are cancelling each other out, interfering in a destructive way. We've got an equation for that one, which is that the path difference is going to be n minus 0.5 minus a half times the wavelength. So if the path difference is like a half or 1.5 or 2.5 times the wavelength, then we get destructive interference going on. So that's going to be the condition for us to get a dark node area on the screen. There's a half wavelength difference, or 1.5 or 2.5, like that. So the example is going to look something like this. Light with a wavelength of 500 nanometers is sent through two slits and reaches a screen. To reach point P, light from slit 1 has to travel 50 micrometers, and light from slit 2 has to travel 52 micrometers. Would this point be a bright antinode or a dark node? So we want to figure out, is the path difference going to be a whole number times the wavelength, or is it going to be like a half number times the wavelength? And then if we know that, we know if it's bright or dark. So we've got our path difference equation, the absolute magnitude, let's call it, of the distance difference between slit 1 to P and slit 2 to P. From slit 1 to P is 50 micrometers, from slit 2 to P is 52 micrometers, so the path difference between them is going to be 2 micrometers. One of them travels 2 micrometers further than the other one does. Now, that's micrometers. We turn that into meters, so micro is 10 to the negative 6, 2 times 10 to the negative 6 is our path difference, and we plug this into an equation. Now, what we've got here is I've just put that the path difference will be some number times the wavelength. If that missing number n comes out to be a whole number, it'll be a bright area. If it comes out to be a half number, it'll be a dark area. So that's going to be our requirement. Is the path difference a whole number or a half number times the wavelength? Wavelength here is 500 nanometers, so that's where the 500 times 10 to the negative 9 comes in that line. So if we solve that equation, we find the value for n is going to be 4, so that tells us that the path difference is the wavelength times 4, and that tells us that we're going to get, since we've got a whole number for n, we're going to have an antinode, a bright area at that spot on the screen when the path difference is equal to those 2 micrometers. So that's how you can approach this. Find your path difference using the situation that's there. Know what your wavelength is. Sometimes you'd have to figure that out. And then you times the wavelength by a whole number or a half number in order to get that path difference. Depending on if it's whole or half, that determines if it's a bright or a dark area. There's a bit to this, but you get the hang of it with practice. Another link, can't do much with that. Here's a link that would be good to use, but I don't know how to record PowerPoints and web documents at the same time. So basically it's that you've got a situation and you change a few things and see how that affects your pattern that you see, your interference pattern. So when we're talking about our pattern, we're going to talk about how far apart the bright areas are. So we might have our bright areas here and here, and then if we change one thing like say the wavelength, we see that our bright areas are now further apart. So we're basically seeing in our interference pattern, if we change a few factors about that situation, how does the spacing of our interference pattern change as a result? If we increase the wavelength, we get a further apart pattern. If we increase how far the screen is from the sources, then the wavelength, the spacing will increase as well. And if the distance between the 2 slits increases, the spacing is going to decrease. That'll make sense on this when we put it all into one equation. So we've got this equation here, which is for double slit diffraction, pattern, interference stuff, and you're going to be using this quite a lot. It's a very important equation for this sort of topic. So what we've got is delta x, which is what we call the fringe spacing, the distance between 2 bright spots, or could be 2 dark spots, but normally it's 2 bright spots. That fringe spacing is equal to the wavelength of the light times the distance from the slits to the screen times the distance between the 2 slits. Those are our 3 parameters: wavelength, distance from the slits to the screen, L, and distance between the 2 slits, how far apart they are, D. And we just plug those into our equation, and that's going to do a lot of stuff for us. So an example is like this. You've got light of wavelength 650 nanometers. It's shone through a pair of slits which are separated by a distance of 100 micrometers. The pattern is observed on the screen, which is 20 centimeters from the slits. So what would the distance between the adjacent bright bands be? What would the fringe spacing be in this case? We just grab our equation from before. We want to find the distance between the bands, which is going to be delta x. We plug in our wavelength of 650 nanometers. We plug in our distance to the screen, 20 centimeters, converted to meters, so 0.2. We divide that by the distance between the 2 slits, which is going to be 100 micrometers, 100 times 10 to the negative 6 meters, and that gets us out 0.0013 meters. So that would end up being what, 0.13 centimeters, something like that, very small number, 0.013 centimeters, I should say, do my conversions right. So it's a bit hard to show this without the picture, but without a better picture, but you've got your light coming in with a wavelength. That's easy enough to visualize. You've got basically the distance between the 2 slits and the screen if you go horizontally across, so that's something that you can hopefully see. And the 2 slits, the top one and the bottom one, there's a distance between them, and that's what the distance D is going to be in this case. So if you're getting told what these numbers mean, so it's easy enough to put them into the equation, but understanding what they mean is something you're going to have to do as well. So that's what those numbers L and D are going to designate: distance to screen and distance between the slits. Now, this will be the final slide. You've got some nice pictures there. This is an experiment that was developed by a guy called Young, and he had this model of how light's going to behave as a wave because it does this double slit interference sort of thing. Initially, there was a bit of resistance to the way he explained this, saying that light was a wave. Basically, the argument against his theory that light was a wave was that if his explanation was true, then the picture at the left should actually occur, where there should be a bright spot observed in the middle of the shadow behind an object, because the light from the different sides of that object should interfere constructively when it moved around, diffracted around the outside of the object. So picture on the left, you've got light coming in, it hits some object, that object casts a shadow area behind it where there shouldn't be any light. His opponents basically said in the center, the path difference should be from the top and bottom should be 0. There should be a bright spot there, and we don't really see that, so surely that can't be the way things work. However, eventually with careful enough equipment, you can actually see, like in the picture on the left, there is going to be a bright spot behind an object. So in that picture on the, sorry, I should say picture on the right, in that picture on the right, there was a circular disc, light was shone in front of it, and then the amount of light behind it was observed. There's obviously a dark shaded area where there's a shadow and no light's getting there because it's blocked by the circular object. In the middle you can see that little dot where there's interference, constructive interference, and the light adds together to get you that bright area. So it's a bit of confirmation that his theory was right, that he predicted something would be there, and then when the experiments were done carefully enough, it was observed that that thing actually was there. So good affirmation of his theory. So that's going to be it for today. This is one of the tougher things to get your head around, but it also forms a big part of this area of study. Double slit interference is like the big thing that you see as part of this, so make sure you're getting on top of this. You can always go to those links that are available and play around with the apps that are there. I would recommend it just to get a handle on what they actually mean and what they convey. But that's basically going to be it. Make sure you're completing the questions from Chapter 9.2 and the associated checkpoints questions. It's from the Lesson 7, the question plan. I'm going to be uploading the next question plan for our next topic. I've still got to finalize bits and pieces, but the idea is that you'll be working on that rather than doing the SAC. And then once we get back to school, we can decide on the SAC and when it's going to be and all that jazz. But for now, you should just be finishing off this topic, and we'll worry about all the other stuff another day.